Hello everyone, welcome to this lecture. In the last lecture we studied two applications of experimental analysis and we saw that how the experimental model identified through model testing can be used for response simulation and force identification. So in this lecture we are going to look at another application of experimental analysis, and that application is local structural modification. So what is local structural modification? So local structural modification is a method to predict the natural frequencies and mode shapes of the modified structure due to a structural modification using the model of the unmodified structure. So if there is a structure and then we want to know that if any structural modification is introduced in this structure, then what would be the changes in the dynamic characteristics, what would be the new dynamic characteristics. Then this local structural modification method enables to predict the new dynamic characteristics based on the model of the unmodified structure, right. So this is the basic idea behind local structural modification method. So this method is also called dual model space method. So when we study its formulation, then we will be able to understand that why it is called dual model space method. Now the question is that what is the application of this capability to predict effect of structural changes on the dynamic characteristics. So this will be useful in the process of dynamic design. So dynamic design refers to the design of a product or a system to ensure that it has acceptable dynamic characteristics and or acceptable dynamic response. When we say that a system has good dynamic design, which means that its dynamics is sound and it has favorable dynamic characteristics. So it does not lead to appreciable dynamic response when dynamic forces which are expected to act on the system in practice would act. So this is the objective of dynamic design, to realize a system or a product with sound dynamics. So now what are acceptable dynamic characteristics and what do you mean by acceptable dynamic response? So the acceptable dynamic characteristics may relate to the specification of acceptable natural frequencies, mode shapes, FRFs and damping factors. For example, there may be a requirement that there should be absence of natural frequencies in a certain band of frequency, so that the resonance could be avoided. So maybe that the excitation forces predominantly act in that band of frequency, right. So this could be one requirement. Other requirement could be associated with the desired mode shapes, right. We may like to have, let us say, the node of a mode at a certain location. We may like to locate anti-resonances at certain frequencies, so that the responses at those frequencies are small. We may like to have desired damping factors, right. We may like to increase the damping factor in certain modes. So this could be the definition of desired dynamic characteristics. Similarly, the acceptable dynamic response could be in terms of permissible displacement, velocity or excitation levels. So when we say that the dynamic response is acceptable, what we mean is that the levels are within the permissible limits, right. So this is what we refer to dynamic design, right, that we would like to have acceptable dynamic characteristics and we would like to have the acceptable dynamic response. So now how dynamic design is carried out. So this flow chart essentially tells the generic steps which are involved in the process of dynamic design. So the process of dynamic design generally starts after an initial design of the product or the system has been worked out, right. So you can see the first step here in the process of dynamic design is that availability of an initial design. So this initial design may be worked out based on failure criteria related to the static strength, fatigue strength, rigidity, wear and so on, right. Now it is difficult to incorporate dynamic design requirements at the stage of initial design, because the dynamic characteristics, they depend on what is the geometry, what are the dimensions, then what are the material properties, what are boundary conditions. So all these things, they determine the dynamic characteristics. So unless the initial design is established or initial design is available, the dynamic characteristics remain undefined. So that is why it is generally difficult to take into account the dynamic design requirements at the stage of initial design, and hence the dynamic design is carried out is after the initial design. So now this dynamic design is carried out by incorporating only minor modifications in the structure, right. So if the initial design does not satisfy the dynamic design requirement, then some modifications to the design are carried out, right, and those modifications are generally minor in nature, so that the initial design is not compromised, because the initial design has been based on certain criteria. So those failure criteria should not be violated when dynamic design is carried out. So that is why the modifications which are done in the initial design to achieve the desired dynamic characteristics are minor in nature. For example, maybe some lump mass may be added at some point, right, or at some points. some lump stiffness may be added, some viscous dashpot or damping may be added. So, these are the minor modifications that are generally done in order to achieve the desired dynamic characteristics. Now, to carry out dynamic design, there could be two approaches. One could be a test based approach, other could be a model based approach. So, in the test based approach, whatever modifications are incorporated, then they are physically incorporated into a prototype based on the initial design, and then the dynamic tests are carried out to see whether the dynamic design requirements are satisfied or not. But this would require large number of physical tests, right, and it is going to be pretty uneconomical and time consuming. So, therefore, a preferred approach is a model based approach, where we build a model and a mathematical model of the product of the system based on the initial design, and then we incorporate the proposed modifications into that model and then check whether the dynamic design requirements are satisfied or not. So, you can see, so we therefore would like to have a mathematical model here based on the initial design. So, this model can be based on finite elements, right, it could be a finite element model or a numerical model. Other possibility is to have or use a model identified through model test, and that would require a prototype based on the initial design to be built and then model tests carried out on that prototype. So, in the context of discussion in this lecture, we are assuming that this model has been identified through model test on a prototype of the product based on the initial design, and that experimental model is then further used. So, now current dynamic characteristics based on the initial design, they are compared with the desired dynamic characteristic, and then they are compared, and if the current dynamic characteristics are unacceptable, then some structural modifications are planned and they are introduced into the model. Now, this is the place where this role of local structural modification method we are going to discuss comes into play. So, here comes the need to predict the effect of these structural modifications on the dynamic characteristics. So, here we have a experimental model and then we have the structural modification that is being introduced, and based on these two pieces of information we would like to determine what are the modified dynamic characteristics of the product based on the initial design. So, this is the application of the local structural modification method we are going to now discuss. So, this is how the dynamic design is carried out. Let us now look at the formulation of the local structural modification method. So, now here the situation is that we have a structure, right, and this structure we are going to refer as an unmodified structure, and then we would introduce certain structural modifications into the structure, right, and then the structure gets modified, and then we call that structure as the modified structure. Therefore, now we have two structures, one is the unmodified structure and other is the modified structure, which is obtained after introducing structural modifications. So, let us first of all write the equations of motion for unmodified structure, then we will introduce the modifications, and then we will write equation of motion for the modified structure, right, and then we will try to see how the dynamic characteristics of the modified structure can be obtained from the knowledge of the dynamic characteristics of the unmodified structure and the definition of the structural modification. Therefore, for the unmodified structure, the equation of motion under free vibration can be written like this: mx double dot plus kx is equal to 0. So, in this equation we have ignored damping, right, but if damping is to be incorporated, formulation can be done by incorporating that. So, here m and k are the mass and stiffness matrices of the unmodified structure. Now, for free vibration the solution can be given by this, that vector x is equal to vector phi cos lambda t. So, here lambda is the frequency of free vibration. So, now substituting this solution x into the equation of motion and simplifying, we get this equation, right. So, this equation you can see is the eigenvalue problem, it is nothing but the eigenvalue problem of the unmodified structure. So, here lambda square are the eigenvalues and phi is the eigenvector, and if n is the degree of freedom of the system, then there will be n number of eigenvalues and n number of eigenvectors, and all those can be put into matrix form, giving us the matrix of eigenvalues and eigenvectors. So, this eigenvalue matrix is diagonal, and eigenvector matrix consists of the eigenvectors making the columns of this matrix. Now, we introduce structural modification, and that structural modification when introduced, now we can write the equations of motion, and let us represent the motion or the displacement of the modified structure by vector y, so as to make a distinction between the motion of the unmodified structure which has been represented by vector x. So, the equation of motion of the modified structure is this. So, m plus delta m y double dot plus k plus delta k y is equal to 0. So, here delta m and delta k, they represent the change in the mass and stiffness matrices because of the structural modification. So, if a structural modification is introduced, in general it would change the mass and the stiffness, right, and therefore delta m and delta k represent the changes in the mass and stiffness matrices due to the structural modification. So, now what we do is that to solve this free vibration of the modified structure, we would transform the displacement vector of the modified structure to the modal space of the unmodified structure. So, earlier we have studied the modal transformation, right. So, we use the eigenvectors to go from physical space to modal space, but in this case we are going to use the eigenvectors of the unmodified structure. Let us do that transformation. So, this is vector y is equal to matrix phi into q. So, here phi is basically the eigenvector matrix of the unmodified structure and y is the displacement vector of the modified structure, and vector q is the vector of modal responses of the modified structure in the modal space of the unmodified structure. So, now we substitute this transformation into the free vibration equation of the modified structure, then we pre-multiply by phi transpose, and then we use the orthogonality properties of the eigenvector of the unmodified structure. So, when that is done and simplification is done, we get this equation. So, you can see this equation now is in the modal space of the unmodified structure, right. So, this equation, matrix equation, is in the modal space of the unmodified structure, because the eigenvectors of the unmodified structure were used for the transformation to modal space. So, here Q is the matrix of modal response in the modal space of the unmodified structure, and then you can see now we have here two coefficient matrices. This is the matrix, this can be called as mass matrix in the modal space of the unmodified structure, and this could be called as the stiffness matrix in the modal space of the unmodified structure, right, or this can also be called as modal mass matrix and modal stiffness matrix, but they are in the modal space of the unmodified structure. And here you can see the this is of course a unity matrix, but this phi transpose delta m phi, it is not a diagonal matrix, it is not a diagonal matrix. Similarly, this lambda r matrix is a diagonal matrix, it is a matrix of eigenvalues of the unmodified structure, but phi transpose delta k phi, which is this is not diagonal. So, therefore, these equations in the modal space, they are not uncoupled equations, they are coupled equations. So, now we would like to solve these equations in the modal space. So, we assume a free vibration response in modal space like this, vector q is equal to vector psi into cos beta t. So, here beta is the frequency of free vibration, right. So, when we substitute this in this equation and simplify, then we get now the eigenvalue problem. So, you can see this is the eigenvalue problem, right. So, this is the eigenvalue problem defined in the modal space of the unmodified structure. So, here beta square is the eigenvalue and psi is the eigenvector. Now, one thing we should see here, the matrices which make up this eigenvalue problem, what those matrices are. So, first we have this matrix, right. So, this matrix, what does it consist of? It consists of the eigenvalue matrix of the unmodified structure lambda r, right, and it consists of the eigenvector matrix of the unmodified structure, that is phi, and it consists of the delta k, basically the description of the structural modification, right, the stiffness description of the structural modification. Similarly, this matrix, it also consists of the eigenvector matrix of the unmodified structure and the description of the mass matrix change due to the structural modification. So, therefore, to solve this eigenvalue problem, what we need is the modal characteristics of the unmodified structure and spatial matrices describing the changes in the mass and stiffness matrices due to structural modification. And if the modal model identified by model test on the unmodified structure is available, then we are left only with delta K and delta M, right, matrices, and they can be then described for the chosen structural modification. So, this eigenvalue problem therefore can be solved without needing the mass and stiffness matrices of the unmodified structure, right. It only requires the model characteristics of the unmodified structure, which can be obtained by model testing. So, that shows us the application of the experimental model analysis for local structural modification. Now, this eigenvalue problem can be solved and it will yield eigenvalues and corresponding eigenvectors, right, and these eigenvalues and eigenvectors can be put into matrix form. So, basically giving us the matrix of eigenvalues and matrix of eigenvectors corresponding to the modified structure. Now, these eigenvalues, eigenvectors, they correspond to the modified structure. But one thing we should note here, the eigenvectors we get, that is the matrix psi, it is defined in the model space of the unmodified structure. So, this matrix psi does not tell us the eigenvectors or mode shapes of the modified structure in the physical space, it is in the model space of the unmodified structure. So, that is why you can see there are now two model spaces involved. So, we have the model space of the unmodified structure and then we have the model space of the modified structure. So, there are two model spaces which are involved here in the solution, and that is why this method is also sometimes referred as dual model space method. So, then how do you determine the eigenvectors of the modified structure in the physical space, right. So, we make use of this transformation that was used, y is equal to phi into q, right. So, here q basically represents the displacement, So, here q basically will be an eigenvector when the free vibration occurs in a particular mode of vibration. So, therefore, all eigenvectors in the physical space can be obtained by product of matrix phi and matrix psi. So, therefore, the eigenvector matrix in physical space would be matrix Z, and that is nothing but equal to matrix phi into matrix psi. So, this is the formulation of the method, and we see that by solving the eigenvalue problem using the model of the unmodified structure and the delta M and delta K matrices for the structure modification, the eigenvalues and eigenvectors of the modified structure can be obtained. So, let us now consider some of the modifications that typically can be incorporated, and effects of those modifications can be predicted using this local structural modification method. So, one such modification is lump mass modification. So, lump mass modification means that we are adding a lump mass, say m naught, at jth degree of freedom. Now, for this modification we should therefore determine what is delta m and delta k. So, delta m is a matrix of order n by n, where n represents the number of elements in the mode shapes of the model of the unmodified structure. So, that represents the number of measurements that were taken to find the model of the unmodified structure. So, this delta m matrix essentially is a matrix of all zeros except the element at the intersection of jth row and jth column. So, you can see this is the jth row and this is jth column. So, this element you can see it is non-zero and it is equal to the lump mass that was added. So, that is delta k. Now, practically the addition of a lump mass will have a negligible effect on the stiffness, and that is why here we can write delta k as a matrix of order n by n, and it is basically a matrix of all zeros. So, this is how the lump mass modification can be described using these special matrices. Let us now look at what is lump stiffness modification. So, lump stiffness modification involves adding a lump spring of stiffness say k naught between the ith and jth DOFs. So, between the ith and jth measured DOFs, lump stiffness k naught is added. So, what will be now delta k matrix for this modification? This is the delta k matrix. So, it is a matrix of order n by n, right, and then we have the stiffness values k naught, minus k naught, minus k naught and k naught, which is stiffness matrix of a linear spring, right, with 2 degrees of freedom, displacement at its both ends, and then these values they correspond to ith and jth rows and ith and jth columns. So, at the intersection of these rows and columns we will have k naught, minus k naught, minus k naught and k naught. So, if mass of this lump spring is small as compared to the mass of the modified structure, then delta m can be taken as a matrix of zeros. Otherwise, delta m can also be suitably taken to account for the change in the mass due to the added spring. Another possible modification is a beam modification. So, beam modification is like addition of a stiffener into the structure between 2 points. So, the beam modification is a more complex modification. So, when a stiffener is added, it not only resists the forces at those points, but also the moments at those points, right, and therefore, the stiffness and the mass matrix of the beam involves both the translational and rotational degrees of freedom, and they can be then described using the finite element matrices for the beam elements. But the difficulty is that there would be inconsistency in the orders of the matrices phi and delta m and delta k, because in the model test generally the measurements are taken only at the translational degrees of freedom, and therefore, the mode shapes in the model model generally have the elements only corresponding to the translational degrees of freedom. The rotational degrees of freedom they are not present in the mode shapes identified through experiment or through model test. So, that is why the matrix phi will not have the rotational degrees of freedom, but they are present in the delta m and delta k matrices. So, there is an inconsistency. So, one approach that has been proposed in the literature to deal with this inconsistency is to expand the measured mode shapes to incorporate the rotational degrees of freedom in them. Let us now summarize some key observations about the local structural modification method. So, first thing we observe is that this method requires the model of the unmodified structure and spatial description of the mass and stiffness changes due to structural modification. So, this method does not require the mass and stiffness matrices of the unmodified structure. So, therefore, the experimental model can be used for predicting the effects of structural modifications on the dynamic characteristics. But one constraint is that the structural modification can be carried out only at the n measured DOFs, because the model is based on measurements at n DOFs, and therefore, the modifications that are introduced, the lump mass modifications, stiffness modifications or other modifications, they can be introduced at and between the points which belong to these n DOFs. Also, the local structural modification method considers only m modes of the unmodified structure, correct. So, if we saw that when we transform to the model space of the unmodified structure, the m number of modes that were identified in the model they were used, but the structure has more modes than m, right, though they were not part of the model identified through model test. So, therefore, some modes are missed when that model transformation is done, correct. So, therefore, it leads to some error due to model truncation, and therefore, that will have some effect on the accuracy of the predicted dynamic characteristics. Another application where the model identified through model test can be used is in the coupled structure analysis. So, in the coupled structure analysis, the idea is to and objective is to obtain the mathematical model of the assembled structure by combining the models of the individual components or substructures of the assembly. So, here if there is a huge or big structure and having several components or substructures, then first the component models are made, and then component and substructure models they are combined to obtain the model of the complete assembled structure. Now, in the context of coupled structure analysis, what is the relevance of experimental analysis? The relevance is that if for some components the numerical models are not available, then they can be replaced by models obtained by model test. So, this coupled structure analysis is also referred to as substructuring. So, one possibility is that all subcomponent models they are derived by model testing, and the models of the individual components then they are combined to obtain the model of the complete structure. The second possibility is that the individual subcomponent models they come from different techniques. For example, some may be built using finite element method, and some may be obtained by model testing, and these models are then combined to obtain the model of the assembled structure. So, this is basically an hybrid approach for coupled structure analysis. So, in this way we come to the end of this lecture. So, in this lecture we talked about local structural modification method, which allows to predict the effect of structural modifications on the dynamic characteristics. We also talked in brief dynamic design, and also saw that what is the role of local structural modification method in the process of dynamic design. Thank you.